Okay, so I know I said in the next video, which I guess you don't know is this video that I'm making. You could watch them in any order. So I guess you can see by the time when they're posted. I know I said in the next video that I was going to continue and show why a quintic polynomial and higher degrees in general cannot be solvable with radicals. I'm going to come back to that. But before I do that, I want to take a brief excursion, which is going to let us think about field extensions a little bit more, which is something that will be important. And that excursion that I'm going to take is I'm going to show the impossibility of doing one of the classical things from ancient Greece in terms of constructions with straight edge and compass. Okay, so what I want to do is show you cannot double the cube with straight edge and compass. Okay, so in other words, if you have a cube where the volume is equal to 1, okay, let's say you know a cube, you know it has one of its vertices at the origin and another vertice at 1, 0, 0, 0, 1, 1, and 0, whichever one I missed. So something like this. These are the axes. You have a cube with vertices right here. I'm going to try my best to draw it, but this is not going to go well. Okay, so that cube right there, okay, what that point, it's 1 away from the origin, that point's 1 away from the origin, that point's 1 away from the origin. And then when we say something like double the cube, what we mean is find the coordinates for a point. If we keep this coordinate here, if we keep that coordinate at the origin, or that vertex at the origin, we want to find a cube double the volume and find the vertices for those points, or find the coordinates for the vertices of those points. Okay, so what this involves doing then, well, if this point right here is, let's say this is the x-axis, is going to be, sorry, I guess this is the y-axis when we write it like this, and this would be the x-axis. This is 1, 0, 0. Okay, if we want to expand the cube so that the vertex is now here, and it's at a, 0, 0, then the volume of the cube is a cubed, and we want this to equal 2 times the volume of that cube, which is 1. And so what we need to do is we need to find the third root of 2. We need to find a third root of 2. As we saw before, there are 3 third roots of 2, but 2 of them are non-real. So obviously we only care about the real one. Okay, and so what I'm going to do is I'm going to explain why we cannot do this with a straight edge and compass, and kind of what that means. Okay, so the first thing I want to point out is the following. This is sort of a definition. So we're going to look at a field extension. So if theta is not in Q, then we can look at this field extension A plus B theta such that A and B are in Q. If this is a field, well, even if it's not a field, this is a vector space over Q of degree, of dimension 2. So for example, when we solved x squared minus 2, and we adjoined the square root of 2, or we adjoined the theta, which we were thinking about as being the square root of 2, that gave us a vector space of degree 2. If in addition this is a field, then we say that this is an extension over Q of degree whatever the dimension here is, in this case 2. Okay, now in the case that we're interested in, we can remember this from the previous video, we also have to add theta squared. okay? And we saw, again, A, B, and C need to be rational. And we saw, in this case, that this doesn't give us all of the roots, but it does give us one of the roots, which is all we care about at this point. We just want to find an extended field that contains one of the roots. This is a vector space over the rational numbers. When we say over the rational numbers, that means the coefficients are rational numbers. And so here the basis vectors are 1, theta, and theta squared. Okay, so what we're saying here is that if we have, this is a third, the dimension of this set as a vector space over Q is 3. And so if this is a field extension of Q, then the degree of that extension is also 2. Or sorry, is also 3. Okay, so I want to look at something that we didn't look at in the last video, because in the last video we were concerned with polynomial degrees, or sorry, with irreducible polynomials. But now I want to look at general polynomials that are maybe, well, we can do what I'm about to do with irreducible polynomials as well, but it's a little bit easier to do what I'm about illustrate when I'm about to illustrate with reducible polynomials. So let's look at the polynomial p of x is equal to x squared minus 2 times x cubed minus 2. And let's say we want to find the field that contains all of the roots of this. Okay, so we're going to basically do this in 2 steps. So we're first going to look at F1. Okay. What I want to do for F1 is I want to adjoin to Q. I want to adjoin the square root of 2. And now I'm going to get all numbers of the form A plus B times the square root of 2, where A and B are in Q. Okay, now this does not contain any root of x cubed minus 2, but it does contain both roots of x squared minus 2. Okay, then what I want to do is I want to get at least one root of x cubed minus 2. So I'm going to say F2, I'm going to say is equal to F1, and I'm adjoining the third root of 2. Okay, and so for this to be a field, it's going to be of the form A plus B theta, I'm going to call this theta, plus C theta squared, where now A, B, and C are in F1. Okay, and so notice what happens. The degree of F1 over Q is equal to 2. The degree of F2 over F1 is equal to 3. And there's a notation for that. The degree of F1 over Q is equal to 2. The degree of F2 over F1 is equal to 3. Okay, now this is not a Galois extension because we still don't have all of the roots. Okay, but that's not especially relevant to what we're talking about. Okay, but now the question is, what about the degree of F2 over Q? I was about to write that as F naught, which is also appropriate, but I didn't say that's what F naught is yet. Okay, so what is the degree of F2 over Q? Okay, well, I would say it should be 6, right? Because we're just going to multiply these two. Okay, but let's maybe come over here and think about this a little more carefully. So what is A? So A has to be in F1. So it has to be of the form, let's see, I'm going to write it like this. A1 plus A1 plus A2 times the square root of 2. Okay, that's what, if A is in F1, it has to be of that form. And then we're going to have plus b, I'm going to write this as b1 plus b2 square root of 2 times theta, and then plus c1 plus c2 square root of 2 times theta squared. Okay, so now what we can do, so we can write this out in the following way, where all of these coefficients, a1, a2, b1, b2, c1, and c2, those are all in Q. Okay, so now we can write this out in the following way. We can write this as a1 plus a2 square root of 2 plus b1 theta plus b2 square root of 2 theta plus c1 theta squared plus c2 square root of 2 theta squared. Okay, so when we get down to this point right here and we write it out in this way, we see that all of these terms are equal to not equal to each other. They are all like different elements in this field extension. So like this right here, square root of 2 times theta squared is a different element from the other elements. Okay, it's like before, if theta, when we did theta was equal to the square root of 2, we didn't have to include theta squared because theta squared is equal to 2. Okay, but none of these, the square root of 2 times theta squared or theta squared and so on and so forth, none of them are in Q. None of them are rational numbers. Okay, so we have to write it out like this. And again, if you take that for granted, if you just believe me for a minute, you will see that in fact, yes, the field there are 6 elements in the basis here. We've got square root of 2 times theta squared, and so on and so forth. Okay, and in general, this is what's going to happen because as you sort of unwrap the definitions like this, we're going to have at this right here, at this point right here, we have a plus b theta plus c, where a, b, and c are in F1. And so this is a vector space of degree 3 over F1, and then F1 is a vector space of degree 2 over Q, and so we can sort of do this multiplying of degrees. So this is equal to 6. Okay, so in general, as we take field extensions, as we go from, let me erase this. As we take field extensions, let's say F0 is a subfield of F1 is a subfield of Fn, then the degree of Fn over F0 is a product of the degrees. So Fn over Fn minus 1 times all the way down to the degree of F1 over F0. Okay, so this is going to be important for the following reason. What does it mean, algebraically speaking, what does it mean to construct something with a straight edge and compass? What does it mean to construct something with a straight edge and compass? Well, what are you doing when you construct something with a straight edge? Well, you're just basically drawing a line between there and there. And so if you draw 2 lines and see where they intersect, then algebraically what you're doing is solving a system of linear equations. You're solving a system of linear equations. Okay, and if these have rational, if both of these have rational, if you write them in terms of rational numbers, ax plus by equals c, where a, b, and c are rational, then their intersection is also going to be rational, because if you just think through about how you're going to solve the system of equations, it's all involving the field operations. So you're not going to go outside of the field, just staying inside the field by doing field operations. The other thing that you can do is if you have a straight edge and a compass, you're going to be doing something like this. You're going to be looking to see where they intersect. That's what happens in a straight edge and compass construction. do things like see where they intersect. Well, this is solving a system of one linear and one quadratic. Okay, but that just reduces to solving, a quadratic equation. And similarly, if you look at where two circles meet, like if you intersect, what you would get not a line in a circle, but two circles, that is going to give you another intersection of quadratics. Okay, so what we do here, when you do something like solving, a straight edge and compass construction, a straight edge and compass construction involves solving linear and quadratic equation. So each step we're solving a linear and quadratic equation. And so what that means is either the solutions are already in the field that we're thinking about, or we have to add them to the field. If we add them to the field, well, we're not going to have to add them to the field if it's linear equations, but we might if they're quadratic equations. And if we add them to the field as a quadratic equation, the extension is going to be 2, going from one field to the other field. So if you start with the field of rational numbers, you're going to have Q, and then maybe you do one construction, and that the point that you construct from that is not in the rational numbers. So you extend to a field, to F1, and since it's a quadratic extension, it's going to be like this one, okay? So a quadratic extension, the degree is going to be 2. And then maybe you do some things in F1, in these classic straight edge and compass constructions, there's many steps that you do. If you want to do this sort of thing, you first start by doing this thing with a straight edge, and then do this thing with a compass, and this other thing with a compass, and then you're going to draw a line from the line that you started with to the intersection of the two circles and that sort of thing. So there's this set of this algorithm that you do, and each step you're either drawing a line and connecting that, or you're drawing a circle and seeing where they intersect and stuff, stuff like that. Okay, so maybe you do a few more steps and you don't have to add anything, and then finally, and then you do another step, and you solve some quadratic equation by intersecting a circle and a line, and so you get another field extension, but now it's an extension over F1, and that degree is also going to be 2, and you do this over and over again. And so you do this as many times for as many steps as there are, and finally you're going to get, let's say, Fn plus 1 as a degree over Fn, as an extension over Fn. And so what this tells us then is the degree of Fn plus 1 over Q is equal to 2 to the n plus 1. So anytime we do a straight edge and a construction with a straight edge and compass and take field extensions step by step by step, the last field that we end up with, that's going to include all of the numbers that we constructed in this process. The extension of that field over the rational numbers has to be a power of 2. Okay, well, why is that a problem? What happens in the case of the cube root of 2 is the polynomial x cubed minus 2 is irreducible over q. Now, that's something that needs to be proven. Okay, but I think we all agree. I think we can all agree that this is irreducible over q. But again, you have to use something to prove it. Eisenstein's criterion, for example. But it's irreducible over over q. This is irreducible over q. So now what we need is, if we want to construct the cubed root of 2, we need to look at Q with that appended to it. And that is a degree 3 extension. That's what we saw right here. Well, not for that example, but we saw in the previous example, in the previous video, we saw that the degree of this extension is 3. So the degree of this extension over Q is equal to 2. Okay, I'm sorry, is equal to 3. I keep saying the exact wrong thing. The degree is equal to 3. Okay, well, so that means that we cannot get to this field via straight edge and compass construction because this is not a power of 2. Okay, so again, this idea of field extensions, we're only adding square roots. So each time we do a field extension, we're just adding a square root of whatever field we're in. And now we have a new field that's whatever we started with a square root adjoined, and we do another construction. Maybe we're adding a square root of those elements, and so on and so forth. But we're never going to add a cubed root. Okay, so that is it for that video. And now I think in the video after this that I make, I will discuss about the general unsolvability of a quintic equation.